Welcome to this next video in which we are discussing the group of units for a ring. Okay, so in this next video then what we're going to do is complete this example of trying to find the group of units for the ring, which is the quotient ring of the integers by the principal ideal generated by n. And we're now assuming that n is some natural number, i.e. you can use 0 if you like, but the ideal that you'll get is just the 0 ideal, and then you'll just be quotienting the integers out by the 0 ideal, and then you'll just get the integers. Okay, so you'd just be asking for the group of units of the integers, which we've already done. So we are now assuming that n is some natural number, some positive integer, rather than 0. Okay, so firstly then, let's have a look at just a quick reminder of the structure of the ring Z mod nz, and then what we'll do is we'll face the problem of which elements in this ring are actually going to be units. Okay, so a reminder then firstly of Z mod nz. So what you do then is you generate the principal ideal generated by n, which will be all integer multiples of n, and then you partition the ring of integers up into the additive cosets of this principal ideal generated by n. Okay, and you end up with n different cosets, and we normally name these cosets according to a representative from them, and the representatives we take are usually in between 0 and n minus 1. So we usually use 0 bar to actually represent the principal ideal generated by n itself, 1 bar, 2 bar, and then it will go all the way up to n minus 1 bar. You won't want n bar because that's the same as 0 bar. Okay, so this notation is the common notation where you put the representative from the coset underneath the bar, and it should be read as the coset that contains this representative. Okay, so these are my different cosets that I've partitioned the ring of integers into then. 0 bar, 1 bar, 2 bar, all the way up to n minus 1 bar. And of course the way that addition and multiplication works on here is through representatives. So if you want to add two cosets together, the way you do it is you take a representative from the two cosets that you want to add together, one from each of them, add them together in the initial ring, which is the integers in this case, and then get some answer in the integers, and then just take the coset that contains that answer. And it's the same for multiplication. If you want to multiply two cosets together, take a representative from both cosets, multiply them together in the initial ring of integers, get some answer, and then take the coset that contains that. That's your answer. Okay, so that is how we add and multiply then in this quotient ring, this modular arithmetic ring. Okay, right. So what we're now considering, of course, is the group of units of this ring. So we want to know which of these cosets is actually a unit, which of them has a multiplicative inverse in the ring. Okay, now of course we know that 0 bar, the additive identity, will not have a multiplicative inverse, so we can instantly cross that one off. And we also know that if we're actually working with Z mod a prime Z, so if n is a prime natural number, then we end up actually with a field, and all the other elements are going to be units in that case. But we're now trying to generalize this. We're now talking about what if n is just some general natural number. Okay, we're now asking the question which elements are units in that more general case, and it's more tricky than in the limited case where n is just a prime. Okay, so we're going to ask them which of these elements is indeed actually a unit, which of them has a multiplicative inverse. Okay, so the way I'm going to do this, rather than trying to derive the result, I think in this case it's better to do statement and proof, so just chuck the result out and then actually try and prove the result. Okay, so let's do this. So here comes the great claim that we're going to spend the rest of the video trying to understand why it's true. Okay, so the claim then is that a coset, okay, which we'll call a bar, is going to be a unit. So a coset is a unit, and of course a, this representative, it will be greater than or equal to 1, and now it will be strictly less than n. Okay, so I've chucked 0 bar out. I'm not interested in that. We know that that's not a unit, so we're not even going to bother with that one. Okay, so a bar is a unit, and here's the claim: if and only if. Okay, so it's the same statement as saying, what is this other statement? That this representative a and n are relatively prime. So a and n are relatively prime, and I will explain what is meant by relatively prime if you're a little loose with what that term means. So a and n are relatively prime in the ring of integers. So a and n are both going to be elements of the integers, and they're going to be relatively prime in the integers. So these two statements are exactly equivalent to one another is what I'm claiming. Okay, so if you want to know which of these cosets are going to be units in the quotient ring that we've formed here, all you need to ask is which elements between 1 and n here are actually relatively prime to n, and it's going to be the cosets with those as a representative that are actually going to be units. Okay, right. So firstly, let me just explain what relatively prime means, because that's going to be very important that we do at least understand what that means. Then I want to remind you a little bit about the correspondence theorem, or what's also called the third isomorphism theorem, because we're going to use that to prove this statement here. But firstly, let me remind you of what relatively prime means. So, a and n are called relatively prime if they're only common divisors are units in the integers, so 1 or -1 in the case of the integers. Okay, so let me say that again. A and n are called relatively prime if the only common divisors, the only thing that both of them can be written as a multiple of, are units, okay, i.e. 1 or -1, and there's a lovely way of stating that in terms of ideals, okay? So if you've got a common divisor, so let's say we've got D, which is a common divisor of A and N, then if you consider what the principal ideal generated by D is going to contain, it must contain both A and N if it's a common divisor of A and N. So if D is a common divisor of A and N, then both A and N must be in the principal ideal generated by D. Okay, that's quite simply because being a common divisor means that A is a multiple of D and N is a multiple of D. Okay, so this is the set that contains all multiples of D, so they must be contained within that set. But of course we know that this is an ideal in the integers. Okay, so that means that if you've got any element that's in an ideal, all of its multiples must also be in that ideal. So what we can say, in fact, is that the entire ideal generated by A and the entire ideal generated by N must be contained within the ideal generated by a common divisor. Okay, so this is the way in terms of ideals that you can state that D is a common divisor of A and N, that the principal ideal generated by A and the principal ideal generated by N are both contained within the principal ideal generated by D. To say that they are relatively prime, or rather, if they're not relatively prime, then it would be the case that you could find some common divisor that was not a unit, okay, some element which generated a principal ideal which was not the unit ideal. Remember, any unit in the integers, 1 or -1, will generate as its principal ideal the entire integers, i.e. you can find some element or some principal ideal in the integers which is properly contained within the integers, which contains the ideal generated by A and the ideal generated by N. The statement that A and N are relatively prime is the statement that there is no such proper ideal that contains the principal ideal generated by A and the principal ideal generated by N and is itself properly contained within the integers. The only ideal of the ring of integers which contains the ideal generated by A and the ideal generated by N is the unit ideal. That's what, in terms of ideals, it means for A and N to be relatively prime in the integers. Now let me just remind you that all ideals in the integers are principal ideals because it's a principal ideal domain. Okay, so we don't need to worry about whether there are ideals that are not principal. Okay, I can now just say that if these two elements, A and N, are relatively prime in the integers, it means there is no ideal that contains both the ideal generated by A and the ideal generated by N and is properly contained in the integers. The only ideal of the integers which contains the ideal generated by A and the ideal generated by N is the unit ideal, which is not a proper ideal. Okay, so there's a little exploration of what it means for these two elements to be relatively prime in the integers, and this is the meaning that we're going to actually need in order to prove this. Okay, so next up what I want to show you is the correspondence theorem, or at least remind you of the correspondence theorem. I'm not going to prove the correspondence theorem in this video. We prove it in the video on maximal ideals earlier in the playlist on ring theory if you'd like to see a more in-depth discussion of it. Okay, but we are going to completely rely on the correspondence theorem in order to prove this, so I do want to just remind you of it. So the correspondence theorem is also called the third isomorphism theorem of rings, but I think the correspondence theorem is a better name for it because it tells you exactly what it's about. It's about a correspondence, a bijective correspondence between the ideals in a quotient ring and the ideals that are in between the ideal that you've quotiented out by and the unit ideal of the initial ring. Okay, so let me describe what the correspondence theorem says then. So let's draw a picture of some ring that we've got here. So let's say this is our ring capital R here. Okay, and we are now going to quotient this ring capital R out by some ideal. So let's say we've got some ideal down here, which I'll call capital I, and I'll colour this in green here. So I is an ideal here, and we're now going to quotient the ring R out by I. So of course what we'll do is we'll divide R up into the cosets, or the additive cosets of the ideal capital I, and of course this is exactly what we've done for the integers, which is why this theorem is going to be useful here, okay, because we're dealing with quotient rings here. Okay, so we partition the ring capital R up into these additive cosets of the ideal capital I, and these additive cosets of the ideal capital I become the elements of the quotient ring now. So the elements in R quotient out by I are the additive cosets of the ideal. Again, the addition law and the multiplication law is exactly the same as it was in here, i.e. it's done through representatives. You take a representative of the two cosets you're trying to add them together in the initial ring, and then take the coset that contains the answer in the initial ring, and the same for multiplication. Okay, right. So what does the correspondence theorem say? The correspondence theorem speaks of a correspondence between the ideals in this quotient ring, okay, where the elements are now the cosets here, and the ideals of the initial ring that contain the ideal capital I, okay? So what this says is that if you have some ideal in here, now what should I call that? I'll call all ideals in the quotient ring by bars. So let's say we've got some ideal I bar, and I probably wasn't the best choice to use because we've used I for this. How should I denote this better? Okay, maybe I should make up my own. I'll colour it in. So we'll have the ideals, the new ideals, coloured in a different colour. So we'll have them coloured in purple. So the ideal that we originally quotiented out by, that one will be coloured in green here. That's a very special ideal. Okay, I'm going to use the same letter, but now I'll colour it in pink. So this is a very different ideal now. So this is some ideal within the quotient ring, and it's barred to show that it's in the quotient ring. Okay, so it's some ideal in here. Okay, so it's a set of the elements in here, so it's a set of cosets, because the elements in here are cosets of the original ring here, okay, which actually is an ideal in this quotient ring. Then the correspondence theorem says that there is a corresponding ideal back in the original ring, which completely contains the initial ideal I here in green that you quotiented out by. So if I draw a picture on here, it might have a corresponding ideal that might look like this. Okay, so I'll colour it round in pink here. So this might be the corresponding ideal of the initial ring, and as I say, it will have to contain the green ideal here that we quotiented out by to produce the quotient ring here, always. And we'll call this ideal now I unbarred. So every ideal in the quotient ring has a corresponding ideal back in the initial ring, which completely contains green ideal that we quotiented out by. Okay, so I'll put it in there, and which itself is obviously contained in the initial ring capital R. Okay, and the way that you'd go from here to here is we know that the elements here are going to be cosets. So if you wrote this out, this would be cosets. You might have 0 bar, that would be the coset containing the additive identity. You might have another coset A bar here, so let's say this is A, this is the coset containing A. You might also have B bar, here's the coset containing B. And the way you'd actually go from having this ideal here, which is a bunch of cosets from the quotient ring in a set here, to this ideal here, which is obviously elements of this original ring, capital R, is you just say, okay, what are all the elements in all of these cosets? So 0 bar is an entire coset, that contains loads of elements. A bar is an entire coset, that contains loads of elements. B bar is an entire coset, that contains loads of elements. Union them all together, all of those cosets, and that will give you the entire ideal back here, the unbarred pink ideal here. So unbarred pink ideal is the union of all of the cosets, okay, that are in I bar. So how should I put this? I'll just put union of all of the cosets in pink ideal bar here. Okay, so that's how you'd actually go from having an ideal here to going back to an ideal here. Now, I'm not going to prove that you'd actually end up with an ideal if indeed you do that. I proved that in the video on maximum ideals. This is just meant to be a reminder of the correspondence. Okay, so every ideal here corresponds to an ideal in between the ideal in green that we quotiented out by and the unit ideal of the initial ring. And it also works the other way around. If you have an ideal unbar in pink here that properly, or not necessarily properly contains in the entire ideal green here and is itself contained in the ring capital R, then it will have a corresponding ideal over here. And the way you'd go this way this time, we've described how to go from here to here through this mechanism. The way you'd go from here to here is you'd say, okay, this is a additive subgroup of the entire ring capital R, and this green ideal, this is going to be an additive subgroup of the pink unbarred ideal. Because remember, all ideals are always additive subgroups. So this is an additive subgroup, green ideal is an additive subgroup, pink ideal is an additive subgroup. So green ideal is an additive subgroup of pink ideal. So we can then quotient pink ideal up into the additive cosets of green ideal, because remember, the way that you partition, it just depends on the addition. Multiplication has nothing to do with the partitioning, it's an additive partition. Okay, so truly, here we have a group. You can view pink as a group in its own right. Get rid of the outside bit if you like, if that makes it easier for you to understand. You've now got a subgroup here. You can just quotient that pink group up into the additive cosets of the green subgroup here, and those cosets will be the same cosets that you'd get if you viewed this as part of the larger ring capital R, which you were quotienting up into cosets. So you'll just get a subset of the cosets that are formed here, and that subset of the cosets that you form, that will be your subset of the quotient ring here, which forms your ideal. So that's how you go from here to here. And the correspondence theorem basically says, you know, that they're in bijective correspondence. For every ideal here, there's a corresponding ideal that's between green ideal and the entire ring. Okay, and for every ideal that's in between green ideal and the ring capital R, there's a corresponding ideal over here. They're in bijective correspondence. That's the correspondence theorem, or the third isomorphism theorem of rings. And we are going to use that and apply it to this quotient ring here, Z quotiented out by NZ, to prove this. Okay, so let's now actually use this to prove this then. So, we need to prove if, and we need to prove only if. We will begin with if. Okay, so, we want to prove that if this is true, it implies that this is true. Okay, we want to prove that if it's true that A and N are relatively prime in the integers, then that implies that A bar is a unit. Okay, in the quotient ring Z quotient out by NZ. So how are we going to do this? Well, of course, we're going to start with our starting assumption that A and N are relatively prime in the integers. And remember, in terms of ideals, what that means. That means that there is no proper ideal in the ring of integers which contains the ideal generated by A and the ideal generated by N. And what we're going to do is we're going to do it by a proof by contradiction. We're going to suppose that this isn't true, that the green statement here isn't true, that A bar is not a unit. and we're going to arrive at a contradiction. We're going to show that actually a and n were not relatively prime to one another. Okay, and therefore if they were relatively prime to one another, a bar must have been a unit. Okay, so start with this contradictory assumption that a bar is not a unit, or at least it's going to form a contradiction. So a bar is going to be assumed to not be a unit in, of course, our quotient ring, and I'll just add that on, in our quotient ring, z quotiented out by the principal ideal generated by n here. Okay, right, so what does that mean? Well, that means that if you generate the principal ideal generated by a bar in the quotient ring here, okay, so you generate all multiples of this, that it is a proper ideal of z mod nz. It is not the unit ideal. If it was the unit ideal, if it was the entire z mod nz, that would imply that a bar was a unit. Okay, so a bar is a proper ideal. It's properly contained within z mod nz. Okay, by the correspondence theorem then, that means that there is a proper ideal of the initial ring capital R that completely contains the quotient ideal that you used. Okay, so now what I can do is I can find a corresponding ideal, I, so by the correspondence theorem this is the corresponding ideal, and it contains the ideal that we used to quotient out, which is the principal ideal generated by n. So instead of writing nz, I will now just write the principal ideal generated by n, and is itself properly contained in the entire ring capital R, which in this case, of course, is the integers. I'm sorry I wrote capital R. Okay, of course, we're working now with the integers rather than a general ring there. Okay, the reason I can conclude that this has to be a proper ideal is because this was a proper ideal in here. Okay, the ideal of z mod nz that corresponds to the unit ideal, the entire integers, is of course going to be the unit ideal here. The unit ideal in the quotient ring corresponds to the unit ideal in the entire ring by the correspondence theorem. Okay, so if you have the unit ideal, of course, that's all cosets in the quotient ring, and you can see evidently that if I took the all cosets, I could draw it like this. If I union together all cosets to get back to my ideal over here, then I'll get the entire ring, I'll get the unit ideal. So the unit ideal here corresponds to the unit ideal here. If I've got a proper ideal here, it must correspond to a proper ideal here. Okay, so I have found you some proper ideal here, which is properly contained within the integers, and I know that it must contain the principal ideal generated by m, which is the ideal that we've quotient out by. I don't know necessarily that this isn't the zero ideal, although of course I did say that we were only considering a not equal to 0, so in a way I do know that this isn't the zero ideal, but I'll still just put that it contains this rather than necessarily actually properly containing this. The important point here is that it's going to be properly contained within the integers, the ring of integers. Okay, now what other conclusion can I then make about this ideal capital I? Well, remember the way that I constructed it. I just took the union of all cosets. What is one of the cosets that this is going to contain? It's absolutely going to contain the coset A bar. One of the elements in A bar is going to be A. So I can also conclude that A is going to be contained within my ideal capital I, the corresponding ideal back in the ring of integers that is in between the principal ideal generated by n and the integers. Okay, now if A is in this ideal, of course I know that the entire principal ideal generated by A must be within this ideal. So now what I have just shown you is that there is some proper ideal of the integers which contains both the principal ideal generated by A and the principal ideal generated by n. And because we know the integers is a principal ideal domain, this ideal will be a principal ideal generated by something. That generator of this ideal would then be a common divisor of these two that would not be a unit, because if it was a unit, its principal ideal would be the entire integers. Okay, so I would have disproven them being relatively prime hence. So there, we've reached a contradiction, because of course the starting assumption was that A and n were relatively prime in the integers. So if you assume then that that A bar was not a unit, it leads to a contradiction. So A bar must have been a unit, and there is the proof of the if part of this statement. So we've now proven that if A and n are relatively prime in the integers, then indeed the coset containing a bar here, in the quotient ring is in fact a unit in that quotient ring. Okay, and now comes the other part, the only if portion. Okay, so to prove only if, of course, what we need to do is prove this direction. We need to prove that if a bar is a unit, it implies a and n are relatively prime in the integers. Because if that's true, then the only way this can be true is if this is true. Okay, because if this wasn't true, then this couldn't be true, because if this was true, it would imply that this was true, which is a contradiction. So proving the only if corresponds to proving that if a bar is a unit, it implies that a and n are relatively prime in the integers. Okay, and we're going to do this by a very similar tactic to the way we showed if. Okay, we're going to obviously start with our starting assumption, but we're going to assume the opposite of what we want to prove. We're going to assume that a and n are not relatively prime in the integers and arrive at a contradiction, arrive at the contradiction that a bar cannot be a unit. Okay, right, so we'll assume that a and n are not relatively prime. Okay, so are not relatively prime. Now, what does that mean if they're not relatively prime? Well, of course, we know what that means. We know that that means that there must be some ideal which is properly contained within the integers and which contains the principal ideal generated by a and the principal ideal generated by n. So I'll just write that down here. So that means that there must exist an ideal, which I'll call I, which is properly contained within the integers and which itself contains the principal ideal generated by A and the principal ideal generated by N, and this of course will be a principal ideal generated by some D, and that will be the common divisor that is a non-unit. Okay, so that's what we can say if we're assuming that they are not relatively prime. Now, of course, what we're going to do is we're going to use the correspondence theorem in the opposite direction, because look, I've got an ideal which contains the ideal that I'm using to quotient out by here, and is itself obviously contained within the ring of integers. So there will be a corresponding ideal now in the quotient ring, okay, a corresponding ideal in z mod nz here, which I will call, what should I call this? I'll call this I bar. Okay, sticking with the bar notation. So there'll be some ideal I bar here. Okay, and what is one of the elements that this is going to have to contain? Well, remember how we go from an ideal that contains the ideal that we're quotienting out by to an ideal in the quotient ring. We look at all of the elements in here and partition them into the additive cosets of this ideal here. Now, one of the elements that you're going to have in here is A, okay, because the entire principal ideal generated by A is contained in here. So specifically, A is going to be contained within this ideal. Okay, A, what coset will it end up in over here? Well, it will end up in the coset A bar. So what I can specifically say is that the coset A bar is going to end up in my ideal I bar. It must do, because A is in this ideal. A will end up in the coset A bar. So the coset A bar must be over here because of the way I go from this to this by just partitioning this up into the cosets of the principal ideal generated by N. So I can conclude that A bar is an element of I bar. But if A bar is an element of I bar, then the entire principal ideal generated by A bar must be, not an element, must be contained within I bar. Okay, but I also know that I bar is going to have to be a proper ideal in the quotient ring here, because I was a proper ideal. Okay, so it will correspond to a proper ideal over here. But that's difficult now, because the principal ideal generated by A bar, if A bar was a unit, which was my starting assumption, then the principal ideal generated by A bar must be the entire quotient ring here. But I'm now saying that it's contained within something which is a proper ideal. Okay, so this is a proper ideal, but that's a contradiction. That contradicts this being a unit, because if this was a unit, the principal ideal it would generate would be the entire quotient ring here. Okay, so that's then how we can reach a contradiction this way. So if it's true that A bar is a unit, then it must be true that A and N are relatively prime in the integers, because if they're not, you can reach a contradiction with A bar being a unit. Okay, so we've now proven this statement both ways. We've proven the if and only if. So we now know that the cosets here, where a is between, well, greater than or equal to 1 and strictly less than n, of course we're not even bothering with 0 bar here, we know that that's not a unit. The cosets a bar, which are units, will be those where this representative a is relatively prime to n. So for instance, one of the ones that you can always say is going to be a unit is 1 bar, because 1 will always be relatively prime to whatever n you come up with, because of course the greatest or the only common divisors of that are going to be 1 and negative 1. Okay, because the only divisors of 1 are 1 and negative 1, so the only options as a common divisor are going to be 1 and negative 1. Okay, so 1 bar is certainly always going to be a unit, which of course we already knew, but now this gives you a way of deciding whether the other ones are going to be units as well. You just have to ask, is it relatively prime to n? i.e., is it true that the only common divisors of the two are 1 and negative 1? You don't have any non-unit element in the integers that is actually a common divisor for the two. Okay, so this means now that we know what the size of the group of units of the quotient ring Z mod nz is actually going to be. So Z mod nz, okay, the size of this group of units is going to be the number of integers that are between 1 and n, so greater than or equal to 1 and n, that are actually relatively prime to n. So to work this out, what you need to do is you need to go through all of the integers that are greater than or equal to 1, all of the integers a that are greater than or equal to 1, but strictly less than n. Okay, so you go through all of these integers here, okay, and you ask, are they relatively prime to n? Okay, and if the answer is yes, you add an extra 1 onto this sum that you're totting up. Okay, and then the final answer, then that's going to be how many elements that you're going to have in this group of units for the ring Z mod nz. And there is a name for this answer, okay? Doing this has a special name, and it was attributed first to Euler. So it's called Euler's phi function. So phi of n means exactly this. Okay, you take this natural number n and you go through all the integers a that are greater than or equal to 1 but strictly less than n, and you ask how many of these are relatively prime to n. That is the answer to phi of n. So this function, it's just a name basically to give us something to actually call this number. Okay, this is called Euler's phi function, and it's something that number theorists absolutely love and have got many theorems concerning. Okay, but if this is your first exposure to it, it is at the moment just a definition. It's just a name for the number of integers a that are greater than or equal to 1 and less than n that are relatively prime to n, and you are just going to have to go through and actually work that out.